Hey everyone, welcome back to another video. Today I'm going to show you how to solve this easy problem. Now, why did I say that in a sarcastic voice? Well, you're about to find out in a second. But before we get started, let us solve this problem normally. So let us just copy and paste this input. So 3, and then we'll just put that in our input folder. And let's just, solve the problem. It's just asking for, a power of 2. If you don't know that, just read it over and you'll soon find out that this is pretty much what I'm doing. So that's that. And then you can do a variety of things. You can do this, or if you're feeling extra fancy, we can do some bit shifting. However, that is not fancy enough because once we submit this, well, first of all, it will work for 3. Let's just do it. Oh, there we go. 8, you can see that is our output. So, your intuition might just be submitting it. Let's just submit it. Let's see what's wrong. So let's submit it, and you'll see that there are so many wrong answers. Wow, why is that? I mean, it should work. I'm doing, what it's asking. I'm raising 2 to the power of n and then taking the modulus. What's wrong with that? Well, here's what's wrong. This data type can only hold up to 64 bits. Okay, now hear me out. This is not 64 bits. In fact, this is 255 bits, 447 bits, and this is 138,000 bits. So how in the world are we going to output this answer when our little, data type can only hold 64? Well, that's where modular exponentiation comes to the rescue. So let us do that quickly. So modular exponentiation is the topic of this video, and is the why this problem is very deceptive, because most people will solve it my way and spend hours trying to figure out what's wrong with their code because it looks so simple, and it is, except for it's just your data type, no primitive data type can hold up to 138,000 bits. So here's how we do it. Let's create a function, okay, called mod exp, and then it's going to get the base, the power, and it works for any module, by the way. It doesn't have to be 1 billion. It can be anything. Okay, so let's start by setting our answer to 1, and then let's do some modulus operation. So just like that, and we do if power and bitwise and 1. Now this is actually a pretty simple trick here where it checks if it's odd or even. So no need to do, get the remainder divisible by 2 or not. No need to do that. We can just do this and, because if you look at it here, let's say we have this string of 8 bits, right? This will have to be an odd number because the last bit has to be, 1 or 0. So if it's a 1, obviously it will be an odd number, and if it's 0, I guarantee you for a fact this will be an even number. So that's where this logic is coming from. And okay, so if it's odd, we do answer equals answer times base modulus mod, and then we do power bit shift right by 1, and then finally we do base equals base times base modulus mod, and then we're done. So we just return the answer, and now down here obviously we gotta modify our little program to fit, and that is how you do modular exponentiation. See, it wasn't that hard. So let's go in here and let's change this to 255. So instead of actually, overflowing, it should output, and that looks right to me. It's not giving us a negative number. So that, in fact, is the answer and how you should solve this problem. So let's just submit it just like that. And then finally, we can see that everything is accepted, and in record time as well, hundredths of a second. and everything is, correct. And yeah, so that's how you use modular exponentiation to solve these type of problems, because the first way will give you either a time limit exceeded or just straight up not work. As you can see, it'll just overflow. So yeah, if you enjoyed this video, please leave a like and subscribe, and I will see you in the next one.